So our next session is a seminar session by Professor Qimiao Si in Rice University. Please welcome Professor Si.
Thank you very much. Is it too loud? Is it better? Good. Yeah, so I guess I'm somewhere between thanking the organizers for having me and welcoming everyone to come. But my task is to make some connections with quantum entanglement from the perspective of quantum materials. And I think Vivian said that I should be prepared to be kicked off the Zoom. So we'll see how far this goes. From a quantum materials perspective, we have a different kind of states that are highly collective. And talking about entanglement is not really new. Entanglement quantities have been looked at for many body systems for some time already. But perhaps from the perspective of looking at measurable entanglement, that's fairly new. That's a development that has happened over the past couple of years. And this is also a particularly opportune time that we're living in an era where we can actually show hardware like this that is actually a quantum processor, and we had a year of celebration on these things. So perhaps it's meaningful to make some connections between the highly collective quantum. This thing is not okay. Highly collective quantum materials and quantum entanglement, and going further, quantum information. So one could ask the question in two ways. We can ask the question, what can quantum materials do for new capacities of quantum information? Or one can ask the question the other way around, what can quantum information approach do to help understand quantum materials? So I'm going to spend this time mostly following the second track and using strange metals as a case study. And strange metals is something that has been of interest since the beginning of the high-TC cuprate field, and has extended to a variety, thank you, a variety of materials platforms. And I think in some sense, right now, the topic is undergoing a resurgence, in part because that the emergence of new platforms, and that really only has happened, I would say, starting from the Mori time and other flat bands. I'll briefly touch upon it. But also the development of some really new probes, and I think we'll probably be hearing a bit along that line in the discussion part of this afternoon. And so with that in mind, and maybe I should have finished this page, I will also briefly touch upon this direction, but very briefly in the context of cavity-coupled quantum critical materials. And so this direction perhaps more like dovetailing with what Brian just talked about in the previous talk. So for this issue of what quantum information approaches can do to help further the understanding of quantum materials, what I want to get through is to get to the point where this somewhat busy chart becomes somewhat clearer. So that's where I'm headed. And to get there, let me start from sort of the beginning of many-body physics, when everybody was excited about learning to do perturbation theory in many-body settings. And the surprise, and really by some heroic work of Philippe Nozières and others, is that if you do perturbation theory in terms of bare electron basis, order by order, to infinite orders, fermi-liquid theory is a robust theory. Quasi-particles are resilient. Spectral function, the task is for the experimentalists to measure accurately. The theoretical statement is very sharp. Namely, there's a sharp spectral function, sharp in the sense that the width is smaller than the energy measured with respect to the Fermi energy. So we can define project bare electron into a quasi-particle, or quasi-particle into bare electron whose spectral weight Z is non-zero. And that defines the existence of a quasi-particle. Now, we want to study strange metals, so we want to break this quasi-particle Fermi-liquid paradigm. So if perturbation theory in terms of bare electron variables doesn't work, let's change variables, and turns out that if Coulomb repulsion is strong, there's a very natural way of localizing, physically localizing electrons and using spins as the starting point, as a building block for low energy physics. So if the first way doesn't work, perhaps there's some chance for this way to work. And so this also is not new. In the 80s and 90s, there was an extreme fascination about starting from this different starting point, but nonetheless, to show that Fermi-liquid theory still even follow this route is extremely robust. And I'll briefly touch upon that. The second class of materials which is emerging, which I will not really talk about it, but maybe if I have a few minutes left, I'll briefly touch upon it, is that because of the bands, some bands are more flat than others. If there's a hierarchy in the bandwidth, then we can open up a new regime of interactions where by the scale of the bare bandwidth interaction is still relatively weak. But because of this hierarchy of the bandwidth, we can arrange a regime where the Coulomb interaction is still not too large, but it can be much larger than the width of the flat band. And this regime, it becomes something that seems to be akin to the more canonical flat band materials like heavy fermions. So that's the kind of quantum materials setting that we want to think about. So let me very quickly run through a few things about quantum criticality in metallic settings and the connection with strange metals. And so quantum criticality is canonically considered by having a phase that breaks the certain global symmetry, such as breaking the global spin symmetry, or to be tagged along with breaking the lattice symmetry. Between that kind of ordered phase and paramagnetic phase, and if it's a second order phase transition, there's a quantum critical point. Except that in this setting, I'm going to also talk about critical slowing down that's not associated with the fluctuations of the magnetic order parameter. And this, in fact, turns out that it's associated with something which are more, in some sense, more quantum mechanical in nature. And the Kondo lattice systems have provided a pretty good setting, both experimentally and theoretically, to consider this type of quantum critical point where strange metal behavior develops. And so Kondo lattice is not too unusual. You have a localized spins due to the Mott physics, localization of the f orbitals in real materials, the SPD electrons. Symmetry dictates that the two species can be coupled anti-ferromagnetically. And if this term wins, you have the Kondo singlet formation, and you break apart the singlet correlations in the ground state, you get the things like heavy quasi-particles in addition to the bare electrons. And these heavy quasi-particles will show up again as a sharp peak, except that the area here is very small. Instead of like copper aluminum, where it's 0.9, becomes something like 10 to minus 3. So the small number suggests that's very fragile, and maybe there are some other competing interactions that can tilt the balance and destroy the quasi-particles entirely. So throughout the talk, I'm going to use that kind of illustration quite frequently, which is that you have these two types of degrees freedoms: localized spins coupled to the spins of conduction electrons, and localized spins which are coupled to each other. And so a quantum critical point that can arise in a way that destroys the quasi-particles is to think about the fate of these spins. So we're going to take advantage of the fact that we're starting with a variable that's other than bare conduction electrons. And the Kondo effect, the study of the heavy Fermi liquid that fascinated a generation of many-body theorists, is that you have this anti-ferromagnetic exchange coupling, but it flows towards strong coupling as energy becomes lower and lower. And so the fixed point forms a Kondo singlet, and that's a ground state that supports heavy quasi-particles. But if we have the coupling between localized spins, one can envision that the fluctuations of spins at a given location would influence the fate of spins at the other location. And so that gives the possibility of another fixed point where the Kondo scale doesn't flow to strong coupling. So then you have to have a critical fixed point. So that is realized in a particular way of looking at these Kondo lattice systems with a fixed point, which is interacting in the sense that it's basically dimensional analysis that works. And the consequence of that is that all the microscopic scales has gone to 0. KBT is the only scale in the problem. So in that sense, the driving force of this quantum criticality is not so much of fluctuations of the magnetic order parameter, but it's this very drastic change to the nature of the ground state. It doesn't have to end up being a continuous phase transition between these two type of phases, which seem to be very different. But if it is, that fixed point with KBT as the only energy scale shows up in some important ways. One of which is that something like dynamical spin susceptibility displays h bar omega over KBT scaling, which we now call the Planckian dynamics. And then the critical exponent doesn't have to follow the Landau framework, and turns out to be fractional, and we can actually calculate using various numerical methods to show that it's a fractional, and it turns out to be somewhere around 0.75. And we also have a statement to make that the scaling function is of this particular form. And so this is historically important because many of us, the theorists, got started was this inelastic neutral scattering data that showed h bar omega over KBT scaling with a critical exponent. And my student Yiming, who's in the audience, actually extract this data and plot according to this digamma function, and seems to do a pretty decent job. And the fact that there's h bar omega KBT scaling shows up in, for example, these quantum Monte Carlo calculations of the dynamical spin susceptibility at the critical point, and also in other things, like if an energy scale that shows up in a relaxation rate as picked up by electrical resistivity, it has this strange metal T-linear behavior. But that's only part of it, because this quantum critical point involves the transition from a phase where you have these heavy quasi-particles, which are part of the Fermi surface formation, to the other side, where the spins do not form Kondo singlet, and therefore there's no development of heavy quasi-particles. from the Kondo process, one important statement is that the Fermi surface would jump across the quantum critical point. So even though the transition is continuous, there's something that's jumping, and that has been fairly extensively tested by normal hole measurement and quantum oscillation measurements that which have provided evidence for a jump of the Fermi surface across the quantum critical point. And if the Fermi surface is jumping, if quasi-particle, and the transition has to be continuous, logically, the only way for that to happen is that the quasi-particle weight has to go to zero at the quantum critical point. So there's a complete destruction of the quasi-particles at the quantum critical point. And there's been a number of tests that have been done in the past using Wiedemann, Franz, etc. But perhaps the most direct evidence has come from short noise measurement, which shows that the noise is smaller than what's expected in terms of the quasi-particle picture. And the reduction is almost like the measured value is only almost about 1/3 of the Fermi liquid quasi-particle expected value. This is only one experiment, so there's space for much more of measurements. So for the purpose of this talk, what I want to make a point on is that in addition to the defining feature of T-linear electrical resistivity, there is an emerging profile for the strange metallicity, namely there's a KB linear in T resistivity, in fact, manifests scaling in the form of dynamical scaling, h bar omega over KBT scaling. And there's a Fermi surface reconstruction, which in the heavy fermions, there's a very direct evidence. In other materials like cuprates, there's also some evidence for that to happen. And there's a loss of quasi-particles at the quantum critical point, and there's an enhanced physical entropy in this strange metal regime, which promotes, which can or may promote emerging phases like high temperature superconductivity. Now, this is sort of the direction we've been looking at theoretically, and also very directly collaborating with experimental groups. And one of the things we realized at some point that if you want to talk about the Kondo effect, it's actually not purely in the magnetic channel. After all, historically, Kondo effect was first discovered in a somewhat mysterious way through charge transport measurement, not through spin measurement. So you can play games like rewriting the Kondo interaction in terms of objects that carry physical charge degrees freedom, and they also turned out to be critical. So it's not just a spin that's quantum critical. A spin is dragging the charge to go along with it. And if you think about it, if there's a T-linear resistivity, if that's part of the direct critical behavior as opposed to be the behavior dominated by subleading physics, then there should also be h bar omega over KBT scaling in the optical conductivity. So at least there's one measurement in this heavy fermion quantum critical point was done by John Kono's group here at Rice using the MBE films of ytterbium rhodium to silicon 2 from Vienna group of Silke Pashan, that the terahertz spectroscopy measured optical conductivity follows h bar omega over KBT scaling, which goes well with some earlier evidence that it has existed in the cuprates for something like this kind of h bar omega over KBT scaling. Now, if you think about it, at the end of the day, it's a magnetic quantum critical point. The thermodynamic phase transition goes from the side which breaks global spin symmetry and the side which does not. And yet, so naively, would it be the spin sector which would be quantum critical? And yet, charge sector, or at least the conductivity, is also showing a very direct quantum critical behavior. And so one would be tempted to say that the strange metal is a quantum critical fluid that involves spin charge entanglement. And it was not entirely clear what that exactly that meant, but did set off, provide a motivation to study entanglement aspect of this quantum critical point and the strange metals that accompany with it. So let's go back to the Hamiltonia, where we have two kinds of microscopic degrees freedoms. We have the spin degrees freedoms, and we have the conduction electron degrees freedom. So there are two most transparent sectors of interactions across the species and within the species. So if you want to study entanglement, there's a choice to be made. So the first thing we did was to study the traditional quantum entanglement properties, entanglement measures, such as the entanglement entropy and their various forms. So we can, for example, since we want to talk about, in this case, the most informative thing that happened is across these 2 degrees freedom. So let's talk about we consider mutual information. You pick one of them to be subsector subsystem A, the other to be subsystem B, the rest to be subsystem C, and you can define from the entanglement entropy the mutual information. And we did this calculation between, again, A is the local F spin, B is the local C electron, and the C is the environment. And so we did this calculation. This is the mutual information. On the left is the Kondo screened side. So this is tuning parameter 0, meaning that there's only, in this Hamiltonia, there's only Kondo interaction, and gradually going to the right is when the RKKY interaction becomes larger and larger. So the limit of Kondo interaction only shows a mutual information that essentially saturates this 2 log 2, which is what happens for a spin singlet. So this makes sense. This connects with the canonical picture of the heavy Fermi liquid, whose ground state is a singlet of the spins and conduction electrons. And then as the RKKY dynamically compete, RKKY interaction dynamically competes with the Kondo interaction, this mutual information becomes smaller and smaller, and that's compatible with sort of the correlation way of physical properties studies that was done in the past, which shows that the local moment spins and the conduction electron spins are separated. Except that at the quantum critical point, it's extremely smooth. So if the purpose is to study quantum critical behavior, this entanglement quantity is not particularly useful. So we can ask the question, if we want to go beyond that, the mutual information is essentially a bipartite entanglement. Are there other forms of entanglement, other entanglement quantities that we can consider? And also there's a small problem that the entanglement entropy is very hard to measure in condensed matter settings. So both provide motivation to study multipartite entanglement, which is connected to the quantum Fisher information. So what is quantum Fisher information? Instead of like looking at the entanglement entropy, where the calculator is dividing the system into subunits, we ask, say, a beam of neutrons to partition the system. And quantum Fisher information is basically a variance of some witness, some particular operator that comprises local operators. And these operators need to commute with each other. And if for an operator like that, that satisfies the condition of being a witness, it's basically a variance. So if you study things like quantum geometry, probably this should ring bell. And if it's a variance in many body systems, it's very natural that it can be determined from. All right, so it's connected to the spectral function. It's experimentally measurable. And let's see if this. Right. Right. I just do it manually. Good. So it's experimentally measurable, and importantly, it provides a bound. So the much like the velocity equality test, the protocol with the velocity equality test. So the bounds works as follows. If you determine on Fisher information at zero temperature, there's just a variance, and finite temperature was figured out that it could be essentially just variance, but with a kernel that has this particular form that filters out the quantum fluctuations. And so this is the quantum Fisher information, and they factor out some trivial factors, like if you have a spin operator locally, depending on whether it's spin 1/2 or spin 1, the eigenvalue spread would be different, so we don't want to consider that. If that's factored out, then this M basically is the N, the total number of, if we're using, suppose we're using spin operators, it's the total number of spins divided by M, that's the cluster, and within each cluster, it's M squared, how the factor of M shows up. So if you get a normalized quantum Fisher information density, that's to some value M, then you're getting the M+1 entanglement. So we're going to look at the quantum lattice form following this protocol using this operator, because this operator also couples to the order parameter field. And so this deals with the spin-spin correlations. And so this is the calculated result of the SZ on the Fisher information density normalized by this eigenvalue spread. So in the string and so it's a multi-part entanglement. So that's the certificate on the ferromagnetic sides. It goes below 1. And so two things. One is that we are on the right track. And this quantum Fisher information is affected by dynamical spin sensitivity, which is experimentally measurable. We should be able to compare with the experiment. And so this is one set of experiment that has recently been very systematically and carefully done in this particular quantum critical heavy fermion material. And this is the measured quantum Fisher information density based on in-glass neutron scattering at the quantum critical point. And you see, so reasonably scale invariant, at least monatomic temperature dependence of the quantum Fisher information. And so our calculation as a function of temperature at a quantum critical point has a fairly similar temperature dependence profile with order of magnitude that's reasonably consistent with the experiment. So that gives some that this quantity is useful. Now, the second point is that what does it mean? So if I have multi-pi entanglement among the local spins, one way to interpret result is that it's basically characterizing something like RVD, like spin entanglement or spin correlations. And so if we have this kind of things in entanglement, the point is this breaks or at least reduce the tendency of the local space forming the singular convection electrons. And remember that local convection electrons is essential for the development of heavy quasi-particle. In that sense, this spin multi-parti entanglement characterizes the suppression of the channel to quasi-particles. So in this way, we characterize this loss of quasi-particles. So it goes back to where I wanted to start, which was to say that this is a control parameter as 0 temperature, and we have a Kondo spring phase, we have a Kondo destroyed phase due to the RKKY interaction, due to the Kondo interaction, and the mutual information calculation provides very direct characterization of pictures like this. And these pictures we had pretty much known in the past without the help of quantum information approaches. But the quantum Fisher information elaboration is new because it reveals this kind of RVB like space-centered correlations and therefore the tendency of the heavy quasi-particles being suppressed. And so now I should emphasize that this is only one witness, one operator, SZ. We could look at other operators, other local operators or other non-local operators to reveal the multi-packet entanglement in other channels. And if you're interested, please feel free to talk to Yuan Fang and for on this aspect, which I will not get into. How much time do I still have? I still have 30 minutes. I'm good. I'm not really no, I think it's probably like 10 minutes. Thank you, though. So I really only want to just give some. I was going to skip this, but since I have 10 minutes, I'll just very quickly run through what can happen with this route of using something like quantum Fisher information and other ways of characterize the quantum information aspect and elucidating the more subtle fluid, like strange metal fluid. So one way to think about heavy fermions is like it's a canonical, it's a flat band system that we've been dealing with for many years, right? And so we've, over the course of the workshop of the school, we've been hearing all the lectures, including ones about flat bands, and typically, in many cases, topological flat bands. And this seems like there's an opportunity to for this something like quantum Fisher information and other quantum information means to clarify some aspects of this quantum physics. So for example, one angle would be that these flat band systems, the cadmium metals, etc., in fact, operate at a much higher temperatures. But still, we have this tension that if interaction is strong, Coulomb interaction is very much local physics because E square of R is the largest when the electron spacing is the smallest. And yet, topology readily expressed in the momentum space. And if we want to go from momentum space to real space, things like topological insulators, like kind of things like Joe talked about, it inherently involves band inversion, so multi-orbital, multi-band physics. And that turns out to be manifested in something like cadmium metals, where you have a hierarchy of bandwidth. And so if we want to treat the effect of strong interactions, turns out that the natural tendency is to utilize a concept called compact localized states, which was worked on, say, 15 years ago or so, except that it's not really a good base, it's not a complete, it's not orthogonal. And so in a particular setting of cadmium metals, we were able to construct the analog of that. It retains the essentially the local symmetry of the compact localized states, but this is a complete and orthonormal and all that. It's a good basis. But importantly, that these compact orbitals have to be coexisting with expanded orbitals. And because of topology, they have to be hybridizing with each other. So in that sense, topology is dictating the hybridization or the quantum fluctuations. And that actually provides a source for suppressing the natural tendency of partially filled flat bands to order something like there's a very nice paper by Joe Moore and collaborators mapping out the possible symmetry breaking orders of, say, the topological flat band. But because the topology enabled quantum fluctuations provides a source for getting suppressing, reducing the tendency towards such order, and thereby reaching perhaps quantum critical point and the strange electron behavior. And there's a number of materials, including ones worked on by my colleague Amy locally, that has showing the tendencies of using quasi-particles. So these systems it seems like very natural for using something like a quantum fission information to probe them. And maybe there's some progress that can be made. And so this is the kind of category methods that Ming and Pinch and I have been working on, and also connects with, say, purely systems. Not only don't think about topology, but if you want, you can introduce topology into it, and you can break quantum particles, or the other way around. Like in addition to this category particle methods, you can think about, for example, twisted WSC2 systems, the recently discovered cyclic conductivity. We've also been thinking about this direction. So this is not the purpose of this talk to go through it, but just to give examples of opportunities, and maybe there's sort of emerging universality, and something like quantum fission information can be a useful tool for such systems. Now, the next 2 or so minutes, I want to go the other way around and touch upon the issue of whether we can utilize the existing elevated entanglement in strange metals in quantum critical systems to perhaps to be useful. And so we heard about sensing. This perhaps is that's as far as we've done to connect with the quantum application front. And so the point is that you can say put cavity to be coupled to junctions and Josephson junctions and other structures. That's the now established platform. You can also put cavity to be coupled to isolated spins. That's a decay physics. And imagine that we start from a quantum critical system, and now we introduce light, such as a cavity, a photon field, to be coupled to the spins. And so if it's a spins, let's consider Zeeman coupling, and then I have choice to be coupled to a number of different spin orientations. But I want to probe the quantum critical fluctuations of the matter field. So we're going to choose this coupling to be with the direction let's use the word sensing the singular fluctuations of quantum criticality. So this model allows us to do that. And again, I don't want to get into details for aficionados of super-radian transitions. The limit where the exchange interaction among IC space to be small, so it's somewhere here, that's the decay transition. So historically, for Zeeman coupling at least, there's no challenge that the decay transition does happen to super-radian phase. Turns out that in this calculation we show, as the work of showed Sir Ely Wang and Monica Mahan-Halley, that if you start from a quantum critical point of the transverse field IC model, infinitesimal coupling to the cavity field will induce a super-radian transition. And at this point, the elevated entanglement of the quantum critical fluid is manifested in a elevated entanglement between light and spin. So that's also interesting. You know, the entanglement enhancement already existed in the quantum critical fluid already. It's just inherited by this light spin hybrid. One thing which is not so trivial not so straightforward is that it turns out that if you are at the quantum critical point of a transverse field Einstein model, you actually don't have much of the spin squeezing in the sense that's perhaps most talked about by the quantum optics community. But in this case, when you start from the underlying quantum critical fluid, put a cavity field to be coupled to it, it turns out that the photon spin squeezing is maximized. It was known that that is enhanced at the decay transition, but the enhancement here has a critical exponent that's even more similar than what happens in the decay transition. So this is something that we've been interacting with all of our AMO colleagues, Katie Hazel and Prue and others to sort of think about this, but also provides an opportunity to connect this real experiment. And so something like cobalt niobium material, which Radu Kodir played with the E8-like physics, and I think Peter Armitage has already done spectroscopy measurements, but certainly this would be a direct way of probing the kind of things that we can do in our calculations in 1D. And if you want to know more, I recommend email one for you to talk to this person on this. So to circle back, maybe this is one way to do things like sensing and other quantum applications by utilizing the quantum materials that are already hosting very strong entanglement and put it in coupling with something like a cavity field or other terahertz field, etc. And maybe that's one angle. I think quantum materials. There's no question that quantum materials will be useful for the quantum information context, but precisely how, probably it's fair to say that at this stage it's not clear, but maybe there's one angle that utilizes the existing entanglement of quantum materials and to do coupling of this kind. So this is the end of the talk. We want to acknowledge a long list of collaborators. So Yu Law, I mentioned Feng Che and Sean Sir, Monica Pankali, Ian Fong, Chen Yuan Di. Their work has been mentioned in parts of the talk. I mentioned the collaboration with Lin Yi and the Pension Dai, a number of former graduate students and postdocs, and collaboration with the long-term collaboration with Kevin Ingerson, also with Maya, who's in the audience, with Jennifer Camel, and the long-term collaboration with the experimental group of Silke Passion and some recent collaborations and so I'll just go to the summary on the screen. Thank you.
Thank you for finishing. Actually, we started 20 minutes late, but you took us back to schedule.
Yeah, so maybe it's more for general theories. In the quantum Fisher information, you can calculate for each individual cubes, right?
Yeah.
So what is actually the differences? I mean, in terms of you get different numbers, right, for different cubes.
Yeah.
That theoretically, how do you understand for different cubes and the different type of numbers you get? What does that actually mean?
Yeah, so I think it's a really good question. It's information that's available experimentally, and it would be good to
I'm asking theoretically.
make sense of it. So, in principle, in the zero time channel, quantum Fisher information is an equal time correlate. So if you recall, in the beginning stage of the cuplate field, there was studies of half field cuplates on correlation length, etc. That was very much extracted from equal time correlators from the
stuff.
yeah. So there's some length scale that you can extract. And you can even study structure dependence. That in principle is different from the correlation events that we normally extract from the based on purely on correlation functions. So we know what quantity it's associated with in the Q dependence. Precisely what it means, I don't think the community has thought carefully through what it gets.
I mean, yeah, I talked to, I mean, Leon Balance, for example, asking about quantum fission. He was basically saying, everything you're doing is just basically multiplies a small factor to the, spin correlation function. That's all you do.
No, I think there's a part,
I mean,
there's a part of it is fair, there's a part of it is not fair. The not fair part is that, if you put two photons, prepare two photons, measure the correlation function. You have all the information about the correlation between two photon fields. But when you convert to something that allows you to say whether this pair of photons are entangled or not, that's a work which is somewhat non-trivial because in the end it was Nobel Prize associated with it, right? So you certify something with the quantum aspect of it by looking at the correlation functions in some particular way.
I mean, in momentum space, any particular Q you do is associated with a landscape, right? I mean, the question is.
I'm saying that it's more than landscape. They normalize, once you factor out the trivial factors, the quantum fission information, the normalized quantum fission information density characterizes the depth of many-body entanglement, the multi-party entanglement in particular. And if you think about, the cold atom community tried very hard. They did prepare this interferometry type of way to measure entanglement. And that's the only measurement of the entanglement that exists for going beyond few particle systems. And I think it's meaningful to look at many-body systems in this particular way. And the fact that, if you have elevated multi-party entanglement and the coupling external objects like photon field, it actually picks up this. I think that there's some physical consequences we can play with.
Yeah, very nice talk. I think you alluded to this a little bit, but if we use neutron patterns for quantum fission from seeing like the entanglement of the spins, you alluded to some. Are we missing the entanglement that's happening in the charge sector or other degrees of freedom? And I don't know, just what are your thoughts on that?
Yeah, so for example, one thing I think we have a paper which is coming out in a couple of days. So if you look at this picture, there's something missing in my statement. So I said that the quantum fission information characterizes the suppression of the heavy quasi-particles in the strange metal regime. In fact, if you look at a heavy quasi-particle, that's also suppressed on the order side. But this SD operator does not pick up that information. So it turns out that if you calculate the quantum fission information of SS or SY operators, that characterizes loss of heavy quasi-particle. It doesn't tell us about loss of light quasi-particle. Then you have to work a bit harder, and that's something that turns out that it's also meaningful to us. What's this particular operator doesn't seem to be doing a particular good job about characterizing the entanglement of firm liquid, because firm liquid by certain entanglement measures, certain measures actually entangled. So we have example as work of eQMA and we have found that you can use some non-local operators through some Jordan label transformations to pick up the multi-party entanglement. But any local operator like string charge doesn't do the trick. So I think that the aspect which actually motivate our work for these quantum critical systems, the string charge entanglement, we actually haven't really addressed it directly. So there should be some charge-related operators that goes in that direction. Yeah, please. Okay.
I just wanted to say that as you well know, but I just make a comment to everyone else. The QFI is a general prescription for dealing with the susceptibility or structure factor, as the case may be here. So you can write it down for the electrical susceptibility as well. And if you do it in a metal, it's infinite. So kind of like the naive treatment that you would bring to the table if you were dealing, like asking to look at charge degrees of freedom, electrical system, but it gives you just an infinite quantity. So it's a different thing altogether.
It's good or it's not good because it doesn't help you too much.
Doesn't help you too much.
But there's so you know, that's the kind of things, in some sense, the optical community, or going back to the generation of many-body physicists, who actually thought through it. Namely, if you have a charged particle, you have long-range polar interaction, right? So if I ask Peter Abamonte to measure density correlation function, he measures certain density correlation function, but you have to convert that into an irreducible density correlation function, which is finite. It's a well-defined correlation function, but it's finite in zero frequency, zero temperature limit, and it has a status of like a local spin correlation function.
I have a question.
We can talk.
Okay, let's think again.